I'll actually do it. 2c plus d equals, I'm going to go real slow here. I look at this as being over 1, multiply top and bottom by 3. So 42, is that right? Negative 42 over 3, and then plus 32 over 3. Put those together, negative 10/3. Okay, 2c plus d is negative 10/3. All right. Two equations, two unknowns, system of equations, college algebra. Do you have any questions? We haven't answered it yet. I was just taking a break, making sure everyone's on the same page. I'm going to now solve a system of equations. So when I write down my system of equations, we usually in college algebra used a brace. C plus d equals 59 over 6. And then the other one, 2c plus d equals negative 10/3. And then you had two methods to solve systems of equations. You either have substitution or elimination. And for this particular system of equations, I would probably use elimination. How do y'all feel about systems of equations? Has it been a while? Okay, we're going to get to a section in this class coming up here in the next month or so where we're going to need to be able to solve systems of equations. Some of them will be 2 equations, 2 unknowns, might be 3 unknowns, might be 4 unknowns, might be 5 unknowns. So what I'm going to recommend is that if you have a graphing calculator, how many of you have a graphing calculator? Okay, how many of those people, are they all TIs, Texas Instrument? Anyone using something else? You have what? Okay, so you have that. What are you using? Who doesn't have a graphing calculator? Okay. You don't have one? Do you have access to one? Do you think you can find someone that has one? You just have that one? You don't have access to one? Okay. I'm willing to, if we just have 1 or 2 students, I might have some that you can borrow for the semester. You have to sign them out or something. What did you have? We'd have to look. But anyway, yeah, we'll have to check to see if that one will do it. Most of these TIs will solve systems of equations. All right, so when we get to that later, just be aware, I'm gonna want y'all to bring them so I can show you how to do it. But we need to be able, a 2x2 system, 2 unknowns, 2 equations, we should be able to do without needing a calculator. So does anyone remember what elimination was? Like how you did this? You try and get one of these to cancel, either the C's or the D's. It's up to you. And I'm going to try and get the D's to cancel because they're just off by a sign. I mean, they're the same thing. I just need to make one of these negative, right? If this was negative D, if I added down, they go away. So I'm going to come in here and I'm going to multiply the bottom equation by -1. And go here, -1, that changes that to negative, changes that to negative, actually changes that to plus, doesn't it? And now add straight down. What happens if you add straight down? Negative C, gone, equals, yes, we have to do that. 59 over 6 plus 10/3. Well, that's not so bad because I can rewrite this as, what, 26ths? Multiply top and bottom by 2, so 26th. And now they have the same denominator, so that's 79/6. And negative C is this, so just multiply both sides by -1. Hey, I know what C is. C is negative 79/6. Once I know C, what can I do? Go back in, plug it in where? Any equation you want, right? As long as it has C and D in it. So I'm going to go back and I'm going to plug it into the first equation. So if I take that first equation, C plus D equals 59/6, and I replace C with negative 79/6 plus d equals 59/6. And add 79/6 to both sides. I got lucky, they have the same denominator. Then I'm going to get 138/6. 148.
Exactly.
It reduces to 23. Yeah, I meant that to happen. Okay. Really, it comes out to be 23. That's just pure chance right there. So that's it. We have C and D. So now you could go back and rewrite that position function, right? All right. Do I need to go rewrite it, or can you go plug those in yourself? Okay. So that illustrates that if you don't have any information about the velocity, you can still get the answer as long as you have two pieces of information about the position, but you might wind up having to do a system of equations.
Would we go back and plug in for S1 and S2, like each problem done separately?
When you what?
Would we go back and do each problem separately? Like, you know how we found them now?
Now we found
go
them.
back and solve this one, and we go back.
No, we found them both. So all you have to go back to is this one right here. Can you read that out to me? It was S of t is it was a t cubed, right?
Yeah.
Plus a half t squared. And then it was ct, right? But what's c? So it's really negative 79/6t. You see that? I replaced the c with that. And then plus d. Was it just plus d? Yep. And d was 23, so plus 23. So that is your precise position function. All right. That's going to do it for 4.7. I'm going to introduce in the last 12, 13 minutes here, I'm just going to introduce you to 5.5, and then we will get more into it next class. Right now, when it comes to finding antiderivatives, our hands are tied. I mean, we really only have a limited number of resources. We have that power rule, and then we have to be able to recognize, derivatives from Cal 1. But other than that, we really don't have a lot. So I'll motivate this idea with a problem. What if we're trying to do the antiderivative? Oops. What's the antiderivative of this? So I'll call this little f of x. Find capital F of x. Can you do it with anything we've talked about? I know some of you can do this because you've seen this before, but can we do this with anything we've talked about? You cannot. You have a product here, right? And so you cannot do them separately, right? And even if you could do them separately, do you know what the antiderivative of this is? If you could do them separately, do you know what the antiderivative of this is? What would your instinct tell you the antiderivative of this is? Sine x squared? Okay, let me try that. It's not, but that's what your instinct would tell you maybe, right? Like, okay, that should just be that. But look, take the derivative of that. What do you get? What's the derivative of this? Cosine of x squared, but then chain rule would also spit a 2x out, wouldn't it? And that's not this. So you're off, aren't you? Okay. So right now, we can't do that. And that's where this next rule comes in. And it's called the substitution rule, or it's really it's a technique, okay? It's called substitution. But before we actually do the substitution, we're going to get some language and some notation straight. It kind of gets tiring to sit there and tell someone over and over, hey, find the antiderivative. Hey, find the antiderivative. Hey, find the antiderivative. And so what we do is we use some notation to let you know we want you to find the antiderivative. So if somebody gives you a little f and they want you to find the antiderivative of it, what they're going to do is they're going to write the function down. They're going to put this symbol in front of it, and they're going to put this symbol at the end. So the two new things are this and this. And when you see those two together, that's telling you find the antiderivative of that function. This symbol out here is called the integral sign. All right? The function you're trying to find the antiderivative of is called the integrand. The whole thing together is called the indefinite integral. This little dx at the end is what we call a differential. And really, I don't want you to get bogged down on this differential, okay, because it can be confusing. I want you to look at it this way. Let's say I started you out with a capital F of x, and let's say it's x squared. What would little f be? 2x, yes? But isn't it really 2x because power rule? 2x, right? And then aren't you supposed to take derivative of what's in here, like the base? What's the derivative of the x in here? It's 1, right? It's 1, but I could write dx to let you know that I did take the derivative. It's just 1. So this is almost like a placeholder that keeps track of the chain rule. Can you accept that? So we're going to look at that dx as really being a 1, but in terms of where we're headed, this is vital for us to be able to keep track of our variables. So it's called the differential. The actual antiderivative, right? We already named that. That's called the antiderivative, capital F. And that c that we keep on getting every time, plus c, plus c, plus c, is called the constant of integration. And all of this stuff that we're doing, trying to find antиderivatives, is called integration. I didn't quote this or underline it, but so we are doing integration. That's like the heart of Cal 2 is integration. Just like in Cal 1, it was differentiation. In some colleges, they call Calculus 1 differential calculus because it's derivatives. And then they call Cal 2 integral calculus. So we're doing integrals, antiderivatives. So that's our notation. And this symbol right here out front, this symbol, this symbol right here, the integral sign, think of it as an S, or if you want, you can say a capital S, that someone took and just stretched out. You're like, well, okay, who cares? The reason why is because this actually comes from the Greek sigma, and it's because the integral later on is going to actually allow us to find areas under curves, and to find the areas we're going to do infinite summations of things. So the whole idea behind this symbol isn't just random. It comes from the idea of the sigma notation. All right? Y'all good? That's just notation. So now I'm going to go back to that example, or I'm going to go and tell you what the substitution rule and strategy is. All right. So let's say that you have an integral. And inside that is your integrand, right? What you're going to do is you're going to look at the integrand. So you're going to physically look at it, okay? Focus your attention on it. And within that integrand, what you want to try and find in there is something. Now you're going to find a lot of things, but you're going to be looking for something special. It's going to be somewhere in here floating around. Maybe it's over here, maybe it's up in the numerator, maybe it's up in an exponent, but somewhere in here is something. And I'm going to label that something by calling it something. That's very unique, clever, isn't it? There it is. So you find it, you see it, you're like, there's something. But if you're going to say that this is your something, you must also see its derivative in there too, somewhere else in the integrand. So when you say, oh, look, I see something, and then over here, somewhere floating around, is the something's derivative. Is that all right for derivative? So you got to see both of them together, something and its derivative, both in the problem. And there's some things about this, the derivative that you have to pay attention to. the derivative of that something should be in the numerator. It cannot be trapped in the denominator. It cannot be trapped under a radical. It must be free up in the numerator. And I'm going to do examples, and you'll see what I'm talking about here, but it has to be free, and it's okay if this derivative that we see up here is off by a constant. If we're off by a constant, it's still good. If you can pull all that off, then what we're going to do is we're going to make a substitution. And we're going to come in here and we're going to replace our something, whatever we saw, we're going to replace it with u. And that's the substitution we're going to make. And I have 5 minutes, so I think I can attack the problem that we were just looking at. Okay, so here we go. We have the antiderivative of x cosine x squared dx. Right? So you look at that, and the first thing you do is you realize nothing that we've learned up to this point can do that, right? So then you say, well, what's next in my arsenal? Substitution, right? That's my next kind of thing. And by the end of this chapter, there will be 5 different things that you can pull out to try. Do you see something and its derivative? X squared. You see x squared? That's your something. What's its derivative? 2x, right? If that's your something, the derivative of it is 2x. Do you see 2x? No. Yeah, kind of. You see x, right? You're off by a constant, right? That's okay, according to what I've said. Did everyone see that? All right, now, what if someone said, no, the something I see is this. I see cosine x squared. That's my something. Why can't we use that? Because what's the derivative of this? Sine, and do you see sines in there? No. So this would not work. Got it? So whatever your something is, which you said was x squared, right? You're going to let u be x squared. You're just going to make that substitution. This can be scratch work I do on the side. Then what you do is you use implicit differentiation from Cal 1. And you take the derivative with respect to x on both sides. So what is the derivative with respect to x here? Du dx. What's the derivative of x squared? Just 2x, right? Okay. And now I'm going to play a little game. What I'm going to try and do is I'm going to try and rewrite this entire problem, and I'm trying to switch it from x's to u's. So one thing I notice is that anywhere I see x squared, I will be able to replace that with what? U, right? So I will be able to swap this out for a u. I need to try and swap out the x dx also, though, and I need it to be in terms of u. So I come back over to my next line here. You see this right here? And I'm just going to manipulate it a little bit. Do you agree with this? I'm just going to kind of multiply by the differential on both sides to move it over here. Yeah? And then I realize that x dx, right, this right here, I have that up there, don't I? If I rewrite this problem like this, because this x is being multiplied, I can slap it to the back, can't I? Like that? Then do you see that the x dx here matches up exactly with this? So let me isolate x dx on this equation, which means you'll divide out this 2 on both sides. And I'm going to write it a little different than division. I'm going to write 1/2 on both sides. So half of this, 2 goes away, half of that, x dx. Go with me, I'm down to 1 minute. Okay, I think we're in business. Let's rewrite this problem. When I rewrite it, my integral sign stays there. Cosine of what? U. And what is x dx in terms of u? 1/2 du. And I can take the 1/2 and I can actually move it out front, but I can even move it like out here completely because it's always just going to come along for the ride. So this becomes 1/2 integral sine cosine u du. And this right here should be something we all recognize. What's the antiderivative of cosine u, right? That's what that's asking. Sine u plus c. Yeah? So this becomes 1/2 sine u plus c. And we're almost done. What was u? X squared, so we switch it back now. That's our answer, but now we switch it back to x squared. So 1/2 sine of x squared plus c. And you can check for yourself, because I'm out of time. Check for yourself, take the derivative of that, and when you do that, you will get this. You'll get this right here. That's where we're headed. You don't have any homework over this, but when we come back to class on Thursday, this is where I'll begin. We're just going to start cranking out substitution problems. All right, everyone have a good day. I was going to say weekend, but I guess I'm getting ahead of myself.
How's that sound?
That'd be nice, right?